Okay, now let's begin. So there was a question that we started in the last session. We'll do that question again. So I'll just go over this recap. Let's just go over the recap before every class so that we are convenient with the notations and all of that. So we had seen what aerodynamic center is. It's the point about which it remains constant throughout the flight duration. CP, the center of pressure, was inconvenient for us to perform our analysis because it kept changing with the flight path angle, with the angle of attack. And so we came up with aerodynamic center to analyze the stability of the system. Right? So aerodynamic center remains constant throughout the flight. Trim was when the net forces and moments are zero. It's the equilibrium point of an aircraft. Then we saw the pitching moment convention, no surface positive, the equation, and the only criteria for stability. Yeah. Then we just some equations, something that you should familiarize yourself with. So you have the wing contribution towards Cm naught. So you have the wing contribution towards Cm naught, tail contribution towards Cm, then wing contribution towards Cm alpha, and tail contribution towards Cm alpha. We saw a neutral point. Neutral point is just the aerodynamic center of the entire aircraft. Will the Cm naught at CL equal to 0 and Cm naught at angle of attack equal to 0 be the same? It will be the same only for a symmetric airfoil, otherwise it will not be the same. Alright? Okay, yeah. So I think we had done a question, something similar that made this very clear. So Cm versus Cl and Cm versus alpha, they have the same pattern of the graph. So your Cm versus Cl will also look like this, and Cm versus alpha will also look like this. It will have the same structure, but it will not have the same Cm naught, alright, except for symmetrical airfoil. Okay. Yeah, so then we saw static margin. Static margin is the amount of, it's how you define the stability of an aircraft. So greater the static margin, greater the stability. Alright. Yeah, so these were just some equations, some terms that were used in the previous equations that will be helpful during the questions. Again, remember the units of the questions are very important. So all of these equations are valid only for terms which are in radians and per radians. So if the question asks for degree or the question has values in degree, please ensure that you do the correct transformation. Okay. Yeah, then we introduced control. Control does not affect the stability in any way. So what it does to the graph is merely translate the graph. It will not change the slope. We know that slope is the only thing that defines stability. So if you rotate, if you just translate the graph, the slope remains the same. Only the CL trim changes. So you can trim it at different CLs. Alright, and the convention was elevator down is positive. This gives you an increase in lift, so CL delta E is positive. CM delta E, this increase in lift at the tail gives you a nose down moment about the CG. So your CM delta E is negative. Then we saw the equation which we used in multiple questions, so you should be comfortable with it. It's how much the elevator should be deflected to trim at the given CL trim. Okay. Yeah, so this was the question that we started in the last session. I think we just did one question from the series, and I said we'll repeat it again. So let's look at it again. Look at the data that's given to you clearly. They've given you the weight of the aircraft, they've given you wing area, and they've given you location of center of gravity. And they've given you data here that is pitching moment about CG versus lift coefficient. So it's CM versus CL at different elevator deflections. So you can see that the slope remains same. The graph is just translated. Okay, so the slope remains the same. So that means this deflection of elevator does not affect stability. Now let's look at the questions. The first question we had done last class, so you should be able to do it quickly. Is find out the stick fixed neutral point. Take about 2 minutes and then we'll discuss this again. We did this in the last session. Just try doing it. So what do you have to do? You have to find the stick fixed neutral point. for that you can use your static margin equation, right? So difference between, so let me just write that down. So you have static margin is minus dcm by dcl. It is also equal to x bar np minus x bar cg. And we need to find this x bar np. Slope you can find out using any of the lines. I think last class what we had used was the first line, which is most convenient, the pink line. So try doing it. You need to find the slope of the line, and then CG is given to you directly, then you can get your neutral point from this equation. You've got D. What about the others? Okay, can somebody guide me through the process? What have you done? How did you get the slope? Yeah, one of you please tell me how you got the slope and how you proceeded with it. So let me see, DCM by DCL, right? We need to find that. How do we find that? From first line we got slope. All right. Okay, perfect. Yeah, this is it. So from the first line you got that equation and it comes to, I think, 0.01. It comes to minus 0.01. Slope is negative. You plug it in here and x bar np is 0.45. I hope it's clear to everyone. All right. This was solved in detail in the last session. Let's go to the next question. Most aft location of center of gravity will be. Correct, because most aft location that the CG can move is the neutral point. So that is the right answer. Is everybody else also clear with this? That the CG cannot go beyond the neutral point, otherwise the aircraft will not be stable. Okay, next. If a pilot wants to fly at a speed of 38.52 meter per second in trim condition, what will be the trim lift coefficient at sea level? How do we go about doing this? First, they've given you the velocity at which he wants to trim the aircraft. So you need to find out CL trim. So first thing you need to do is CL trim. You need to find this out first. Right? That is what they've asked you. How do we find out CL trim? You can use your lift equation. Very straightforward. What was your lift equation? Half rho v square s CL. Now just apply this equation at trim condition and find out CL trim. Alright, quite a lot of you got me. See, it is the right answer. I'll just write the equation for completion. 2W by rho V trim squared by S. So V trim is 38.52. Okay, now let's go to the next question. If a pilot wants to fly at a speed of 34.20, what will be the elevator deflection required? So first step is similar to the previous question, find out CL trim, and then tell me how you will find out the elevator deflection required. So first step, CL trim is 2W by, and note that your velocity is different from the previous case, okay? So it's rho V squared S V trim. And that comes to, find out CL trim first and then tell me how you'll find out elevator deflection. So your graph that's given to you is CM versus CL, and they've given to you at multiple elevator deflections. Try doing it. All right. Is it better now? Okay. Are you able to proceed? Okay, so there are two ways to do this. One is, now that you have CL trim, could you find CL trim? The CL trim I'm getting as 0.999. Yeah. Okay. So one way is to write down the equation of any 2 points, find out CM naught, and see which graph corresponds to that CM naught. Okay, you have DCM versus DCL. We have this quantity, right? We have it as minus 0.15. Now you write the equation of a straight line, and the only unknown there will be CM naught. The 2 points should be, one is at trim location. At trim location. So point number, let me just draw a table here. Take 2 points of the graph. Point number one is trim, right? And point number two is where your CM naught is there. Okay, so for these 2 points, what will your CL and CM be? At trim, what is the CL? Your CL trim, which is 0.99. And CM will be at trim, what will CM be? At trim, what is the value of CM? Zero, correct. So you write zero there. And at CM naught, what will be the value of CL? When the graph is at CM naught, what will be the value of CL? Correct, zero. So now use these 2 points and find out, wait, only unknown is CM naught. You have the slope, only unknown is CM naught. Find out CM naught. What is CM naught? Does it come as 0.1485 or it comes exactly as 0.15? 1 minute, let me just check. Okay, so your CL trim is actually, it's, if you take more decimal places, it goes closer to 1, and I got something as CM naught as 0.149. Correct? So take it approximately as 0.15. Okay. Now you look at the graph and see for which line the graph is at 0.15. Okay, just a minute. Now tell me for which line the, how did we get CM naught? Using the straight line equation, you have 2 points and you have the slope. That's how we got, okay. What is the equation of a straight line? If I have 2 points and the slope, how do I write equation of straight line? Point number one is this and point number two is this. So tell me how you'll write the equation of a straight line. And slope is this minus 0.15. How will you write the equation of a straight line? All right. Okay. Deepashri, did you get it? Equation of a straight line when 2 points are given. So if you have y1, y2, x1, x2, and m, then what is the equation of a straight line? Alright, so I'll just write it for completion's sake. So you have 2 points, dcm by dcl. So 0 minus cm naught by 0.999 minus 0. You can get cm naught as approximately 0.15. Now please look at the graph and tell me which line corresponds to 0.15 as cm naught. Perfect. Yes, minus 15 degrees. So this is the line that corresponds to 0.15 as cm naught. It is 15 degrees upward deflection of the elevator, and that is minus 15. So that is the right answer. Minus 15. Okay, now let's go to the next question. If suddenly a weight of 15 kg is dropped as a payload in flight and pilot wants to fly at same speed of 34.20 meter per second in trim condition, the elevator deflection required when compared to previous case will be more, less, remain same, cannot say. Okay, you wanted the previous question? Alright, you got CM naught as 0.15. Till there, is it clear, Dharmesh? Okay. Now, CM naught for the red line is 0.15. For the green line is something between that, so 0.14. For the dark green line is here for this, and for the pink line is 0. So we got CM naught as 0.15. So the correct line of CM versus CL is the red line. Is that clear? Yes. Now red line corresponds to degrees, 15 degrees up. And according to our sign convention, elevator deflection up is positive or negative? Exactly. So it's minus 15 degrees. Now is it clear? All right. Okay. Okay, let's go back to the next question. Okay, so if suddenly a weight of 15 kg is dropped as payload in flight and pilot wants to fly at same speed of 34.2 in trim condition, the elevator deflection required as compared to the previous case will be more, less, same, cannot say. Try doing this. You'll have to recompute your CL trim because now your weight has changed. Alright? You just have to repeat the previous question with a new weight. Try doing it. Okay, he has gotten less. What about the others? Just give a minute or two for the others to do the question. You just have to do it similar to the previous question and see if the elevator deflection is more or less. Okay, can you tell me how you got to that? What did you do? So you found out CL trim again. How much is the new CL trim? 0.987. All right. So your new CM naught will be 0.148. Perfect. Now this 0.148 will fall somewhere here, and so your elevator deflection is less. Right? You can see the pattern here. So red is 15 degrees up, the light green was 10 degrees up, so it's decreasing. So if this is minus 50 and this is minus 10, somewhere in between will be less than that. So you need to deflect your elevator less. So yes, the right option is less. Let's go to the next question. Okay, yeah, before that, so today we'll start directional stability and control. I think there's some problem with the alignment of the data. Okay, we'll just try to manage with this. Okay, for directional stability and control, what are the conventions? Conventions are right wing back is positive yawing moment, right? So everybody understands that. It's just a recap of what you've studied already, directional stability and control. So conventions, right wing back is considered positive yawing movement. How do we find out that? You put your thumb along the yaw axis, the direction of curl of fingers is the positive yawing movement. Then relative velocity on the right is considered positive side slip. So if I have, this is the fuselage reference line, and if this is your relative velocity, this is positive beta. Okay, so this is relative velocity, this is fuselage reference line. Alright, so this is considered positive side slip angle. And deflecting your rudder to the left is considered positive delta R. Okay, alright. Now for static directional stability, so for static longitudinal stability, only condition was that a Cm alpha should be less than 0. For static directional stability, only condition is that, okay, all of that has not come on this slide, I'm not sure why, but let me just write it. Only condition is Cn beta should be greater than 0. Greater than 0. Right? This is the only condition for static directional stability. Okay. Oh, there is something seriously wrong with the alignment. Let me just try to give a brief recap. So the next session, I'll try to get images of this. Okay, fine. So what this slide contained was that the induced positive beta gives you a positive side force. So you have positive side force Fy, which gives you a negative. So positive beta gives positive Fy and negative Cn. Okay. And therefore your Cn beta is negative. So that is the condition for directional stability. This is similar to your longitudinal stability case. And what are the factors that contribute towards, what are the structures that contribute towards static directional stability? Vertical tail and swept wing. These two contribute towards your directional stability. All right. Okay, there was a neat little table here. Let me see if I can Okay, then this slide was supposed to deal with control. So positive rudder deflection we had already seen is it creates a negative yawing moment, and Cn delta R will be less than 0. So Cn delta R will be less than 0. Alright. So this was a comparison between longitudinal and directional case. Let me see if I can. Okay, Cm alpha less than 0. For directional case, it is Cn beta greater than 0. At trim condition, you have alpha. To trim it at positive alpha, you need Cm naught to be greater than 0. Now, for directional stability, you prefer to trim the aircraft at 0 degrees. So at trim, you want your beta to be 0, and hence your Cn naught is also 0. And here you mostly have a symmetric airfoil, so this is inevitably 0. Now control, in the longitudinal case, Cm delta E was always less than 0, and Cn delta R we just saw is also less than 0. This is a comparison between the longitudinal and the directional stability case. Next we have lateral stability. Here again, okay, convention, right wing down is considered positive roll. Again, you can put your thumb along your stability axis. The direction of curl of fingers gives you the positive moment. So right wing going down is positive roll. Right aileron up, left aileron down is positive rolling moment. Alright. Okay. Now for static lateral stability, the only condition is CL beta should be less than 0. Okay. This is the only condition required for that. Okay, what are the terms, what are the structures that contribute towards lateral stability? Vertical tail, high wing, or a low wing with a dihedral? There is nothing much on the slides because the alignment is all off. I'll try to make better slides, but yeah, you can. Let me know when you're done. Alright. Okay, so vertical tail, high wing, and low wing with dihedral is what contributes towards lateral stability. Now let's look at the questions. Okay, so see the data that's given to you. We have done similar questions for longitudinal stability. So let's see this. Sorry. So they're given the weight of the aircraft, area of the wings, density, aspect ratio of the wing, xCG, xAC of the wing to be the same as 0.3, mean aerodynamic chord, and details of vertical tail. So lift curve slope of the vertical tail in per radians. Please be wary of the units. Then B vertical tail, span of the vertical tail area, rudder efficiency factor is 1, and distance from CG to AC of the vertical tail, that is the moment arm, is 4.5 meter. Tau, control surface effectiveness parameter. In this case, it will be the rudder. Okay, effectiveness parameter of the rudder is 0.4, and they've asked you to find out the aspect ratio of the vertical tail. This is straightforward. Try doing it. Alright, yes, it's 1.6. Aspect ratio is nothing but b squared by s. And you have 4 squared by 10. You have 1.6. Okay, next question. Lift curve slope of the vertical tail in per radians. Lift curve slope of the vertical tail. All right. What about the others? Yes, span efficiency factor is same as vertical tail. Yes. Okay, I'll explain. So it's the relationship between the 2D airfoil and the 3D wing. Okay, Devashri, let me just write down that equation. Just CL alpha 3D equals CL alpha 2D by 1 plus CL alpha 2D by pi E AR. Okay, so this is all in per radians, so you can just easily get it. Is it clear now, Devashri? All right, all right. So now if you substitute it, you will get 2.473. All right, let's go to the next question. Vertical tail volume ratio. Vertical tail volume ratio. Okay. Can you tell me how you got your answers? One person has, two of you have gotten A, somebody's gotten C. So since two of you have gotten A, tell me how you got A. We need to find out vertical tail. First of all, what is the vertical tail volume ratio formula? What is the formula for vertical tail volume ratio? Yes. Okay, so I'm just going to write it as SV, that is the vertical tail area, by S of the wing into moment arm LV by what is in the denominator? Is it C or is it L? Span of the wing, right? D. D is what comes in the denominator for the vertical tail. C bar is for the horizontal tail. For the vertical tail, it is the span of the wing, because the axis has changed now. Your horizontal tail was along the longitudinal axis. This is along the vertical axis, right? So it is the span of the wing. Now can you see where you made the mistake? I think Alvin has got the right answer, C. What about the others? Just try doing it now that you know that it is B. Denominator is B. We need to find out B. So rest of the quantities are given to you. Area is 10. This area is 20. LV is directly given to you as 4.5. Now find out the span of the wing. Yes, now everybody's getting C. Okay, so let's just do it for completion's sake. We needed to use the aspect ratio equation. So aspect ratio AR is B squared by S. Aspect ratio, where was the aspect ratio? Yeah, 5 is B squared by S is 20. And so B you get as 10. Plug that in here and you get C. Correct. Next question. Rudder control power in per radians if the tail efficiency factor is 1. Rudder control power is, what is the notation? Is Cn delta R. So this is what they've asked you to find. Last slide. Okay. Let me know when you're done, Adarsh. All right. Okay. So they've asked you to find out Cn delta R. What is the formula for Cn delta R? It is similar to why we took B. So that is the formula for vertical tail volume ratio. So the wetted surface area will change for the vertical tail and the horizontal tail. So in reference, when we take the reference, so when you derive the equations, why did we start with C bar? Right. So when we derive the longitudinal stability equations, when we took the CM at CG, why did we start with C bar? Where did that C bar come into the picture for the horizontal tail volume ratio? So if it was horizontal tail volume ratio, we had ST by S, LT by C bar. Where did the C bar come into the picture? It came from the half rho V square S C bar, right? So CM was half rho V squared C bar, S C bar, right? There was a C bar in that equation, correct? Similarly, for Cn, the Cn equation, the wetted surface area would be the span of the wing. In that case, your Cn would have a B in the equation. So it will all be divided by B, and your in the horizontal and vertical tail volume ratio, you will have B. This basically happened because your vertical tail is along the negative z, like it's in the perpendicular axis to your horizontal tail, right? So your the wetted surface area changes, so the reference area changes. Okay. Alright. Okay, yeah, so your Cn delta R, what was the equation? B. Okay, let me just write down the equation. Cn delta R is eta V, vertical tail volume ratio, Cy beta, and tau. So Alvin has gotten B. What about the others? Try doing it. Yeah, so Cy beta will be equal to negative of Cl alpha 3d of the vertical tail. Okay, the Cl alpha we just found out. Uh, it will be the negative of that. Why will it be negative? Because let me just draw this. If this is your fuselage reference line and this is your vertical tail. Okay. Now, if there is a positive beta is denoted this way, right? So positive beta creates a force in this direction, correct? Now, according to our axis, your positive y-axis is here. So if I create a force in the opposite direction, the force created is minus Fy. So Cy beta will be negative of Cl alpha 3d. So this Cy will have a negative sign inherent in it. Have the others gotten the answer? Alvin has gotten B. What about the others? Yes, B is the right answer. Just substitute the values directly into this equation and you will get minus 0.22. Alright, let's go to the next question. The speed of the aircraft during landing in meter per second is take CL landing to be 2 and G to be 9.81 meter per second square. This again should be very straightforward. What is the speed during landing? Yes, D is the right answer. So you just have to take the lift equation. So lift is equal to half rho V squared SCL. CL during landing is given to you. You have S, you have density, you have the lift, and you just have to find out the V. So the right answer is this D. Correct. Let's go to the next question. If the directional stability for the above aircraft is C and beta is 0.2146 per radian, maximum allowable rudder deflection is 30 plus or minus 30 degrees, and CL during landing is 2. What is the maximum allowable crosswind speed that can be handled during landing? What is crosswind? So let me just draw the graph. So if this is your fuselage reference line and there is a crosswind happening, so you have this to be beta. This is your capital V and this is your small v. Okay, so this is the diagram. So this is the crosswind. Let me just denote that by W. Okay, so this is, I'm just denoting this by small v because that is the convention that we followed. I'll just write it neatly. Okay, this is the fuselage reference line. Okay, so this is the diagram schematic for the crosswind. Now try to find out the crosswind speed during landing, maximum allowable crosswind speed during landing. What you need to find, so what you need to find out is this small v. They have asked you to find out small v, that is the crosswind here, right? So there is a crosswind that has occurred and your aircraft is subject to a side slip angle beta. Now they've given you Cn beta and the other terms in the equation in the question. You need to find out small v. How do we find out small v? So just take tan beta is equal to small v by capital V. Correct. So during landing, you already found out your capital V. Okay, you just found out yours in the previous question. We need to find out small v. What else is left? Beta. How do we find out beta using the given equations? Try doing it from whatever is given to you in the question. So you just take the equation Cn beta into beta plus Cn delta R into delta R equals 0 to negate to assume that Cn is 0. Alright. So use this equation and then find out beta. So from this we get beta to be about 31 degrees. Okay, and plug that in here. Only unknown is v. V comes to 21 meters per second. Correct? So she's gotten the right answer. She said A. Yes, that is the right answer. Alright, let's go to the next question. Side slip angle for the above case. Uh, we just saw this question, right? So I mean we just found out the side slip angle. It was 31 degrees. So that is that. Let's go to the next question. Okay. During a flight, if the aileron is deflected with a certain positive angle, how will this affect the directional stability of the aircraft? Alright, think again, think again. If I deflect control surfaces, will my stability change? Deflecting control surfaces have no effect on stability, right? We had discussed this several times. Correct? If I deflect the elevator also, there is no change in stability. If I deflect aileron also, there is no change. If I deflect rudder also, there will be no change. Alright, so it is remain unchanged. Okay, be very careful. These type of questions are very frequent. So deflection of control surfaces do not affect stability. The slope of the graph remains same. Okay. Okay. So I think in this case it was CL beta. CL beta. The CL versus beta graph remains the same. All right. Let's go to the next question. The contribution of vertical tail to directional stability depends upon vertical tail volume ratio, vertical tail efficiency factor, both vertical tail volume ratio and efficiency factor, none of these. What was the equation for C and beta? So your directional stability, it depends on C and beta, right? C and beta, what is the formula? We just use this. We use something similar. So it was a minus eta v cy beta 1 plus. Okay, so this was your something equivalent to the downwash angle. It's something similar here. D beta, right? So now this was the equation. Tell me what it depends on now. C. Correct. Alright, let's go to the next question. The aileron control effectiveness depends upon. Aileron control effectiveness depends upon. Okay, previous slide. Yeah, this is the previous slide. Let me know when you're done, Deepashri. Okay. Yeah, aileron control effectiveness depends upon. Aileron is on the wing, right? So it obviously depends upon the lift curve slope of the wing. Alright, let's go to the next question. An aircraft is flying in the south direction at a velocity of 50 meter per second under crosswind from the west to east of 3 meter per second. So crosswind is 3 meter per second from west to east. The side slip angle in degrees will be. So you note that the aircraft is flying in the south direction. That is the trick here. Till now we had defined positive beta depending on aircraft flying in the north direction. So it will be the reverse for south direction. Draw the diagram, the arrow diagram before you do this, and then you'll be able to get it. Just note that it will be reversed for the aircraft flying in the south direction. We had defined positive beta when the reference velocity is on the right? This is always the case. So just look at it from the reverse point of view now. The reference velocity on the right, it's the same thing will cause the positive beta, but just look at it from the south perspective. Okay, Alvin has gotten B. What about the others? What about the others? Correct. Okay, so I'll just draw the schematic. So aircraft is flying in the south direction. So your why is this? Okay, just give me a second. I think the pen has lost charge. Just give me 2 seconds. Okay. So, if the aircraft is flying in the south direction, your relative velocity is your initial velocity is this direction, and your crosswind they said is from west to east. So this is your 3 meters per second. This is the relative velocity, VR, and this is your V, which is 50 meters per second. And now, if you use the tan beta equation, you get V by V, and you get V to be plus 3.433. Correct? Okay. Next question. An aircraft is flying in south direction at a velocity of 60 meter per second under crosswind from west to east of 6 meter per second. If the value of Cn beta is 0.015 per degree, Cn delta R is minus 0.009 per degree, where beta is the side slip angle and delta R is the rudder deflection. The rudder deflection in degrees given by the pilot in this case will be. So this is like an extension of the previous question. Try doing this. You do have to find out your beta. Next, you need to find out how much you need to deflect the rudder. Okay, all of you gotten C. Let's just see how we got it. First, finding out beta is similar. Beta is uh, tan inverse 6 upon 60, and we get 5.71, right? And then you plug it into this other equation. You have Cn beta into beta plus Cn delta R into delta R equals 0. And from there, your delta R you will get as 9.5, right? You need to make sure that your units are matching, okay? All right, so all units are in degrees and per degree, so yeah, you don't have to do much. So it's just 9.516, 9.52. Correct. All right. Next question. Okay, there is no next question. We've come to an end of today's questions. Okay, so do you have any questions? I think next session on Sunday will be our last. We'll just see some more concepts. Is there any other topic that you need to ask me or any questions? Let me know what topics you want discussed, what topics you want more questions from in the next session so we can have more of that. Or if you have any questions right now. Dynamic stability. Okay. Try to bring that up. Anything else? Will the small area on deflection produce favorable yaw? Okay, so the main primary control surface for adverse yaw correction is the rudder. But I don't think aileron will. What do you mean by favorable yaw? So when you deflect the aileron, it does produce a yawing moment also, and you need to deflect the rudder to Fugoid mode. Okay, yeah, I'll look at dynamic stability. Yeah, so when you deflect the aileron, it does produce some amount of yaw, which is why you need to deflect the rudder to maintain it. No, so I think I have a video on this that I'll show you in the next session. I, you are familiar with adverse yaw, right? So there is a video that shows how when you deflect the ailerons while you want it also to yaw in the same direction, it tends to go in the other direction, and which is why you have the rudder deflection. So I'll bring up the video in the next session. Hopefully it'll play here, and then it should be clear. Okay, I'll try to bring that video. Can we include flap effectiveness factor? Uh, so what was the CM naught equation? When you say CM naught equation, I'm not sure what you mean. What equation are we referring to? CM naught of, okay, horizontally. Okay, let's just go to that. This one, right? This one is what you're talking about. You mean flap effectiveness factor? We don't have any effectiveness parameter here. Why will the flap effectiveness factor come into this equation? I'm not sure why you have that question. We have the efficiency factor, we have the volume ratio. Why will the effectiveness parameter come here? Effectiveness parameter is defined by tau for different control surfaces correspondingly, but not sure why you think it will come here. Elevator deflection changes CM naught, so I thought we need to include. Okay, so elevator deflection changes Okay, CM not. Okay, that way. Let me just think about it. Okay, so elevator deflection changes the CM versus CL graph CM naught. It doesn't change the CM versus alpha CM naught, right? That CM naught is different from this CM naught. So even the control surface effectiveness parameter is not on the CM naught equation. So flap effectiveness parameter will certainly be not be there. Okay. For longitudinal stability, which wing is more stable? Will the dihedral wing provide longitudinal static stability? Oh, I had to look into this. I'm sorry, I haven't checked that. I will check it and get back to you. The high wing, low wing configuration, I will check it and get back to you. But I don't think the dihedral contributes towards longitudinal stability in any way because it does not deflect the forces in that direction. In elevator requirement calculation, do we need to take CM naught at alpha equal to 0 or CM naught at CL equal to 0? CM naught at alpha equal to 0. So let me just go back to that equation. So the CM naught, when it says just CM naught, we have defined it as CM versus alpha as CM naught. Only when it is explicitly mentioned that it is not that, we consider something else. Is there a relation between CM naught at alpha equal to 0 and CM naught at CL equal to 0? Yes, so there is a relation between CL and alpha, so you can derive it using that relation, right? So you can take CM can be written as CM naught plus DCM by DCL into CL. CM can also be written as, so this is CM naught 1 and this is CM naught 2. So, sorry, D plus DCM by D alpha into alpha. And we also have the relationship between CL. It's CL naught plus DCL by D alpha into alpha. And you can, now using these three equations, you can derive the relation on your own, right? So you just DCM by DCL, you just rewrite it as DCM by D alpha into 1 by DCL by D alpha and plug it in here. Take the terms from the other two equations and you can derive the equation on your own. Correct? Okay, I'll do that. I've tried to refer to some questions from previous year's questions and try changing the questions. You can also try, I think some of these questions are from the NPTEL courses, so you can try getting the questions from there. Other than that, I think IGC has a pretty intensive question bank, so you can try that. Okay, I'm not sure why the upload is not happening. I'll try it once more. Yeah, have you gotten the download link? Okay, I'm not sure what happened. I've tried one more time. Let's just see. I think the same problem was happening in the demo session also. I've tried one more time. I'm not sure what is happening. I have, but the session is recorded. You can always access the recording, right? I'm not sure how it works. Can you access the recordings? I can upload the slides in Google Drive, but the annotations will not be there. Is that fine? Yeah, I have tried all of that. I've tried converting to PDF this time. The annotations are not on my PPT, it's on the site, so I cannot really download the annotated slides. I tried uploading the PDF also. Let me just try one more time. I think it is enabled. Can you just check download of PDF? It is enabled right now. Oh, that is also error. I'm not sure what I can do now. Let me just try asking Dinesh sir. So the recorded sections don't have the annotations? Is that what you're saying, Alvin? Top portion of slide is not visible, but the content is available, right? Like whatever is on the slides, and those are available, right? Okay, so then I think that should suffice. I'll try avoiding writing on top from next time. I've asked Dinesh sir, he hasn't really responded, but we'll see from next time. I will not write on the top of the slides, but otherwise, the content is accessible, right? So it's recorded and you can access that. That should suffice. Okay. If not, you can ask me anytime over WhatsApp if you have some issue with some particular question. All right. So we'll meet for the next session. I think it'll be on Sunday. We'll meet for that. All right. Thank you.